smoke detectors located in the basement.
Mm-hmm.
Well, on the plan,
Mm.
there was no smoke detector in the furnace room.
Well, now I sort of talked about this, but usually you have combo units where it's like it'll be a heat detector, smoke detector built in together. In fact, these days you can get combo units where it's a carbon monoxide, heat detector, smoke detector, all built in generally. So if you look on it, because they are required, I mean, basically you got to look at your main sources of where this comes from. But yeah, they'll have a like a heat detector slash smoke alarm. So it's
Yeah.
kind of it's a trick question. I got a couple of them.
Okay.
I do it on purpose. Well, it's because I want you guys. I mean, you're looking at the prints. Oh, this says this. It's like, yeah, yeah, it does.
I was looking in the look. There's like the octagon with the S in it.
Yeah, they've got their own little like symbols for the. Yep, yep. And it used to be they would. I mean, when they first cut them in, they were just little battery units you could pretty much install. Zip, zip. These days, though, when you put them in, they require like a 110 hookup with a battery backup kind of thing. But yeah, you get combo units now where it'll be a heat detector slash smoke alarm. The reason being, I mean, sometimes you can have like an open flame going with little smoke, in which case you want to detect the heat, but and vice versa. The earlier the warning, the better off it is for everybody, kind of thing. Uh, so today we are going to talk about chapter 3. So now we start getting into figuring out how we're gonna start wiring things up. I mean, how do we determine how many things we're going to require? We start talking about branch circuits. So when you look at your like service panel, everything kind of trees out, right? So you get feeders, and it starts at the circuit breaker, and the wire travels along and goes somewhere. And then what happens? You'll be feeding, a given branch, and it'll spread out. So I might be with this one breaker, I might be energizing like 3 different lumens or something like that, or so many receptacles. But how do we go about doing that? Well, chapter 3 starts to talk about that. How do we figure out wire sizing and the loading, right? So, I mean, earlier we talked about ampacity, and ampacity is the ability to deliver current. Doesn't mean we're always going to be energized with that amount of current. But when we look at a branch circuit, um, the circuit conductors, right, the wire between a final overcurrent device protecting the circuit and the outlet. And what do they mean by an overcurrent device? Well, that's anything that's going to trip in the event that you have too much current going into a line. Let's say I have a rated line of 20 amps, and all of a sudden it starts pulling more than that, like 25 amps. It has like some kind of hard short to it. Well, you want the fuse to blow, the circuit breaker to trip, or something, to de-energize that to prevent more damage occurring. So your final overcurrent device in this case is usually back in the service panel, and that's your circuit breaker. And that'll basically, what's that? That's your like weakest link, if you will, because now I've set my certain circuit up to be based on that the overcurrent device, right? So if I have a 15 amp breaker in there, then that's my limit is 15 amps. I have a 20 amp breaker and so on. And then we look at something called feeders. Now, a feeder is considered basically all circuit conductors, and by conductors, usually we mean the wiring involved, because that's what the current is going to travel on, between the service equipment, the source, and any other power supply source in that branch. So anything within that loop, right, as I feed out and then come back, because current always has to have a path to go. So that would be considered the feeder circuit, because I'm feeding off of that. So when we look at like a pictorial of it, right? So here we have basically the mast up on the outside of the house being fed in by the power company. Comes in and there's the meter box being fed into some type of fuse box here, coming into my main service panel. This is where I'm going to have the circuit breakers is within here. Now from the circuit breakers, now I feed what's considered a branch circuit. I have one main line coming through to a junction box here being fed out. And so when it spreads out like that, that's considered the branch. It's still all tied back with one circuit, but here we're feeding several different things. So the conductors between the final overcurrent device and the outlets, right? That's considered your branch circuit here. So basically my wiring feeding into this is essentially considered the branch, if you will. Hopefully that makes sense. And again, I always go back and it's ampacity, ampacity, ampacity. It's our ability to deliver. It doesn't mean we're always going to deliver 20 amps. It doesn't mean, well, hopefully, otherwise your meter is going to be going crazy. You know, we're not always going to feed 15 amps or 30 amps or whatever size the breaker is, but we have the ability to deliver that if needed. So my limiting factor here is very typically the overcurrent device protecting that conductor, which is the circuit breaker or the fuse in this case. The only exception typically, you know, primarily within a residence is going to be our motor circuits. And we'll get into that a little bit later, why motors are considered continuous duty and they fall under a different factor. But for typical type things, you know, energizing equipment throughout your house, we deal with ampacity. So, and this one's a biggie. This is probably the most important part of this whole chapter. The amp rating of your branch circuit or the overcurrent protective device, right? In this case, it's either the fuse or the circuit breaker. That determines the rating of that branch circuit. And these are very standard sizes listed here, where we have probably the most two that you'll see the most of within your service panel will be the 15s and the 20s. Those would be the most populated circuit breakers you have in your panels, but you'll also have 30s, 40s, and 50s, depending on what you're delivering to, different appliances and utility factors that you'll have throughout your house. But these ones here are pretty much your standard. And there are exceptions. You may have a device that may require more than that, but very commonly these are the sizes that we typically deal with within a house. So they look through and then got a table that's used for ampacity ratings. You got this, it's in the Uglies book, and it lists off basically the current carrying capabilities of your different wire sizes. So like how much current can number 14 hold, how much can number 12, number 10, number 8, and so on. And they'll have a list, and it's also based on temperature factor. So we look at 75 degrees Celsius operating thing in Illinois, and we go down the line and look at that. And we have to look at the insulation involved with our wiring. So in this case, you have a THHW, and the W indicates a wet. That means this wire is capable of operating in a wet environment. So it's Thermal high with a wet. Otherwise, you'll see a THHN, which is not meant for wet. It just means it has a nylon insulation to it. So THHN and THHW are probably the two most common nylon factors you'll have involved in home wiring. Those will be. There are exceptions to this where you might have a different kind of insulation depending on the environment that it's meant to go into. But very commonly, THHW is meant for, like, things on the outside. If you have outlets outside that you're delivering to or something like that. Within the house, typically it's THHM. But we could go into the Uglies book and look, and so if I were to ask you, what's the ampacity of number 6 THHW wire in conduit? And it would have a rating factor to that. We could look and see what's the ampacity for a single number 10 THHW wire in open air. And again, it's a temperature factor that you're dealing with in this case. So if it's in conduit, that's one factor. If it's just running in open air, that's an entirely another factor. And then, of course, depending on the situation we have, we might have to apply different correction factors, depending, there's certain cases where we might experience a different kind of temperature that we have to worry about. So typically, yeah, running on a rooftop, we have to deal with higher heat, furnace spaces, limited spaces where we expect there to be like heat buildup or something like that. We would have to consider that factor in, because heat is not electricity's friend. The higher the heat, the less current I'm able to deliver. And meanwhile, back at the main panel, the current is still going to attempt to travel down that particular line. It doesn't care about what's in its way, like heat or something like that. And this is generally how we can end up delivering over current. And that's why we have fuses and circuit breakers protecting this stuff. But if we go look through, and we'll find, we could look up table 31015B, section 2, subtopic A, and find that there is code for correction factors. They'll generally have like either A, they'll list it out like in a table format where you can easily look up depending on your situation. Sometimes we might have a little formula involved where you'd have to plug in a few variables like temperature, footage, and that kind of thing, wire sizing. But the NEC is pretty straightforward with that. They like a lot of tables and a lot of charts for people to just be able to look up readily. And next week we'll have an exercise actually where we'll go through and we'll try to size our own circuit. But we do have rating factors that we can apply with the 3 current carrying conductors installed in a single raceway. And it's pretty common. That's we'll have the hot, the neutral, and a ground wire generally traveling to any given circuit. We may have more in a conduit, but very typically this is what we have coming to an outlet, right? Is our three wires. So if we were to look up, let's say in the previous question, right? We can look up what's our ampacity capabilities if we have 8 wires in a given conduit. And these tables and charts are listed, and we can look at what size conduit we're dealing with. If we have 1/2 inch, 3/4, or 1 inch, those are the 3 most commons that we'll have within a house. There are exceptions to that, of course, but we'd be able to look it up and see. It's like, okay, what can we do here? Can we actually run 8 number 14s in this 3/4 EMT, and is that allowed? And again, it's going to be a heat factor. So if it says no, you're only allowed 7 wires in that, then we would have to size up to the next size of conduit in this case to allow more room for expansion for heat. Heat is our big thing we have to think about. But yeah, we'll get into what lighting loads are. They're the typical easiest. Lighting loads don't usually change on the fly. We can go ahead and make branch circuits off lighting loads that go back. Very typically, we're just delivering with 15 amp breakers to given lighting branch circuits. Usually nothing over 20 amps. It really depends though. Sometimes there are like certain situations where they might have like some special lumen installed that's got some crazy wattage to it or something like that, but that would be something to be considered from the plans. Usually you can go through and plan it out, and it's like, because it's low load, the light bulb doesn't burn that much, so usually we can lump up a few different lighting branch circuits together and have them all traveling off of one circuit breaker, if you will. So, general rule of thumb, the minimum lighting load for dwellings is a 3-volt amps per square foot. And that's like a rule. So if you look at your house and you say, okay, I got like 1,200 square feet. So if we were to divide that out, we'd say, oh, 1,200 square feet, and I'm allowed 3 VA per square foot. I could multiply that out and say, well, then I can have X amount. And they consider that because you're going to have, right, you need lights in your house. So they figure, okay, we're going to have X amount of lights for this amount of square footage. And that's how I figure out how I have one circuit for lights or two or three and so on. Oh, yeah, here. Things acting up. So, and again, we always fall back to how does the NEC define it? So they define continuous. It's a load where the maximum current is expected to continue for 3 hours or more. Now, that would be a factor we would have to consider, right? And that's how often do you actually have something that's running in the house for 3 hours or more? Your typical receptacle, I mean, are you going to have a vacuum cleaner plugged into it running 3 hours? Your microwave, is that going to be going for 3 hours and that kind of thing? So the usual answer is no. So where do you expect to actually see something running for 3 hours or more? Well, that's the big boys, usually like your AC and your furnace, that kind of thing. And that's where those things are going to be running constantly in summer and winter conditions, right? So this would be how we would multiply something like that out. We would say, okay, continuous load shall not exceed 80% of the branch circuit rating. So we would have to actually do a little math and see, okay, how do I size my circuit breaker up for that? And there are, and it's special equipment usually, right? Water heaters. If you had an electric water heater, that's constantly, it would have to be keeping the heat going. So that thing is expected to run. Air conditioning equipment, during the summer, that stuff, those little motors kick off for the condenser and that kind of thing. If you get one of those nice driveways where you have the snow melting cables down in the center of it or something like that, those things will run for a really long time. And that's something where we would consider it to be what they say continuous duty. So it's running, more than 3 hours at a time. That's a constant current delivery kind of thing. So when you have that, what we have to do is we have a little multiplier right here where we say, oh, well, then it's 125% of that. So we look and say, well, all right, well, how's our example? We have an electric furnace, and on the nameplate on that furnace, it says it would need a 40 amp breaker through it, okay, a 40 amp circuit. So if that's the case, then we multiply that 40 amps by 125%, we come up with 50 amp. So in our case, if we put a 40 amp breaker in for this furnace, it's going to trip all the time because it's after a while, it's just that current buildup and it's going to exceed the rating, right? So it's going to be pooling because that's continuous duty. So you can see that by multiplying out with this 125. So we go, oh, 40 amp rating, but we need a 50 amp breaker to basically deliver to the, is it going to pull 50 amps all the time? No. But when it's under load and it's running hard and it's running heavy, yeah, it'll probably pull 50 amps, but for a certain amount of time, but it's considered continuous duty. So it does change the way we have to look at a circuit breaker or circuit delivery. So NEC, and again, we have tables. We can even look these up in charts and we can look and, they'll have ratings for it. We can look and go, oh, 50 amps. They already have the map by 125. We'll go, oh, well, we need this breaker size here. And they'll have it laid out for the power distribution, depending. I mean, commonly, you're not going to have these big boys down here. We don't have homes where we have 600 volts average. Usually what we're dealing with is right down in this range, the 120, the 120/240. Sometimes, certain commercial things like stores and stuff, you might run into some of these other configurations. Usually not. And then when you get, of course, into like a factory or something like that, you're going to start dealing with this much higher power. So, but that's other considerations. That doesn't typically go with like, your average house. Your average house, you're dealing with these bottom two right here. More often than not, this 120/240 combination. But so, and just like a little highlight, most public service commissions require the voltage for residential services to be plus or minus 5% of the nominal if they measure it at the service point. And where's the service point? That's coming in where your meter's at. From the transformer to your meter is considered your service point. Because that's where they deliver power to. After that, then of course, now it's your side. Now, after the meter, it's like now it's residential. Before the meter, it's considered service or, the service delivery from the power company. So we kind of we'll look through chapter 3 and we'll see how do we size stuff. Well, you've seen that one where the lighting circuits are based on the square footage of your house. So usually that's how they do that, the general lighting load, unless you have a few exceptions where maybe like in a room you might have like a ton of can lights or something like that. Then you would have to consider another factor just because you have like more than the required amount of lighting that's going to typically go into a room. So that one would be considered like a separate factor. But very much on the average, you would just literally take your overall square footage of your house and plug it through and determine how many lighting branch circuits you're going to need in that house. Very typically, you only have like 2 or 3 lighting circuits going into a house. But again, it depends on the size. If you got a really large house, yeah, you're going to have a lot more lighting branches going through it. And things we don't consider as part of the average, we don't consider the square footage. If it's like an open porch, that's considered outside. A garage or any unfinished areas of the house, you don't typically add those in as your square footage or your usable square footage, because people aren't generally going to be residing in an unfinished area. You may be going down there and require lights, right? An unfinished basement, you might have a workroom or something like that, but on the average, that's not where you have your setups going. And so they don't use that as a factor, I guess you could call it. So they have a steps. How do you do? And our big one, really, our takeaway from this chapter is how do we determine the minimum number of lighting branch circuits that we're going to have within our house? So our first step, what do? So we multiply our occupied floor area by 3BA. So if we have like a 1,200 square foot house, we would multiply it by 3 and we come up with 3,600, right? We could divide that by 120, it would deliver our required ampacity. Step 2. So we take that little number and we divide by a we're going to use our 15 amp circuit breakers. So we're going to divide that up by our 15 amp circuit breakers to see what our minimum number of circuit breakers are going to be. Here's how the formula would work. 3BA times your square foot divided by your 120 would give you our amperes delivered. Amperes delivered divided by 15 gives us the minimum number of lighting branch circuits we're going to need in our house. So when we get something like this, we're going to round up. Even though the number is really small, like in this case 0.08, okay, is small, we're still going to round up to 5. So for this house, we're going to need 5 15 amp lighting branch circuits throughout this house. But again, look, see, we're dealing with 2,450 square feet, which is pretty good sized, right? So we would have 5 different circuit breakers dedicated basically to lights. And there'll be feeders going out, depending on how we do the layouts and whatnot. But that is what our number is going to be. And so this is our first step in figuring out how much power we're going to be delivering to our house and how we're going to populate our service panel. And going through these steps also determines what size service panel we're going to end up needing. Because if we, again, it all comes down to cost factors when we get down to the bottom line, because this is all equipment that we're going to have to purchase and put in as part of our job bid, right? So, the smaller service panel we can get away with, the cheaper the price comes out. but we don't want to undersize. So we have to make sure that we still have enough room for like future expansion and that kind of thing. And we'll show you that as we get into it. But, and then we kind of look at the number of small appliance branch circuits throughout the house. And very typically the kitchen, right? The kitchen is going to run several of our small appliances, our microwaves, toasters, coffee makers, and all that. Pound per pound, the kitchen's got the most small appliances as compared to the rest of the house. The other one that you might have in there as well would be bathroom areas or occasionally like a utility room. But very commonly, the kitchen is considered like your small appliance room, if you will. So if we look at NEC, and we got a couple articles that we have to deal with, they state that a minimum of 1,500 VA shall be included for each small appliance circuit and each laundry circuit. So if we say that, okay, 1,500 VA, does that mean that's how many, and we know we can divide that out. We typically have 120 volts going through the house, so we can divide that 1,500 out by the 120 and figure out how many small appliance and laundry circuits we're going to actually be required to have, right? So in this case, the NEC states that you shall not have less than two 20 amp small appliance circuits serving a kitchen countertop area. So that means that you absolute at a bare minimum, even if it's a super tiny kitchen, are still going to be required to have two 20 amp dedicated breakers, you know, feeding to the kitchen countertop area. Just little considerations, things that they don't normally spell out. You'll see if you look around your house and it's not laid out this way, it's very common. It all depends on who did the wiring, right? But in any case, so if we look at our 20 amp delivery, so we go up a higher current than our 15 amps that we were using for our lighting circuits, because now we're dealing with little workhorses, if you will. And you'll find that 20 amp, you're also going to be dealing with a different wire sizing versus your 15 amp. Very commonly for 15 amp circuits, you're going to be dealing with number 14 wire as your pull. 20 amp circuits are going to be pulling number 12. And after a while, you'll start to see that, you know, for this size circuit breaker, we're going to be pulling this size wire. And it's like a given, because this size wire can handle this much current, and that's it. So if you put in like a 20 amp circuit, right, and you end up putting in a wire too small, what's going to happen over time is you're going to be tripping those breakers all the time, because the wire is going to be trying to limit how much current it can pull. Meanwhile, the circuit breaker is saying, oh yeah, you can handle 20. You'll have a heat factor after a time, and after a while, you know, you'll eventually break down the wiring and end up with some kind of mishap. Hopefully not fires, but anyway. But yeah, the NEC goes through and they do provide minimum requirements that we will need to have for feeding our different branch circuits throughout our house. They have points where at any point along, and again, if you look around your house and you don't have this, you know, you might be dealing with older NEC code when your house was built, that kind of thing. But when we build a new house, there's not any point along any wall within our residential area that shall not have a receptacle less than 6 feet apart. So if you look around your room and you, let's say your room only has like 2 receptacles and you got, you know, a good sized room, it's probably built in an older factor before 1975, when they really started cutting in a lot of the NEC codes here. But in any new dwelling, yeah, we have to plan on bare minimum 6 foot apart. And the reason being is they want to limit the usage of extension cords, because the more extension cords you have in a house, the higher your fire factor goes up by quite a bit, because extension cords are notorious for causing home fires. So if you have a lot of extension cords, I'm very sorry. But but yeah, any wall space, and this is a rule of thumb, you know, 600 millimeters, right? Yeah, metric system. But any wall space 24 inches or more must have a receptacle, and no point along your wall 6 feet apart shall not have a receptacle then it's not required in your plans, then you need to talk to your boss or the architect and tell them, no, we need receptacles here, 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 and here. And you kind of redline it and that kind of thing. Maybe they missed something or something like that. But when you go through and calculate, you do have to look at the house plans and make sure that every point along the walls in residential areas do have this. And the same with kitchen counters have specific rules. And again, limiting the usage of extension cords. You know, if we could get away with a house with absolutely no extension cords, that would be an absolute beautiful, beautiful thing. But yeah, so on the countertop, our rule of thumb is you can't get away with more than a foot until you have another receptacle. So if you go along your countertop and your receptacles are spaced out like 2 foot or more, you know, that's a no-no. Yeah, you'd be amazed at how often this one's overlooked in new builds especially. But yeah, counters, they want to limit extension cords. We're limiting extension cords. But yeah, then if you look along your countertop, you should have no more than a foot from one receptacle to the other. Because that's generally where most of your appliances are within your kitchen. But, and again, any point along a kitchen counter should not be more than 24 inches from any given receptacle. And that means anywhere within that countertop space should it measure out that you don't have at least 2 feet to be able to run a cord. And if not, then you need to add a receptacle somewhere within there to eliminate this, again, eliminating the use of extension cords. And I showed you last time, right, where we install these things. And these are the most common styles you'll see. We'll have a single gang box installed. And sometimes you don't see these too often unless you are going to have like a built-in microwave or something like that. They might have a single receptacle in this case. The most common style you usually see is this style here, the duplex. The simplex ones, not so much, but sometimes. And then you get the quads, right? But again, ground plug up. But these are the 3 most common styles you would have, and this should be on your countertops and in your utility rooms and that kind of thing. And we have another little rule when we deal with countertops or anywhere where there's to be wet. If there's going to be water, then all 125 single phase 15 and 20 amp receptacles installed within 6 feet of the outside edge of sinks shall have a GFI protection to it. Now, that doesn't mean that every single receptacle involved in this is going to be a GFI. In fact, you can't. Typically, what you would have is on one given line, you would have one GFI receptacle as protection to that circuit, and you would have that coming in as being fed by the line. And then there's a separate area that feeds through that GFI that's considered the load, where you could feed other parts of other receptacles with it. But if you were to put on one given line more than one GFI, they'll constantly trip because they fight each other. So on one given little branch, one GFI, and that's pretty much your rule. But yeah, if you're within 6 feet of any kind of running water, you know, edges of sinks, you have to have GFI. You have to have GFI protection. Have to. GFI protection is required for all receptacles in unfinished basements because flood factors. You cannot have receptacles where they're installed into the cabinet with the face going up, you know, water being able to run into the receptacle. That's a huge no-no. Absolutely not. And at least one receptacle shall be installed. And remember, shall in NEC's little library is absolutely must. Shall is their word, meaning you better do this. Shall be installed in the front and another in the back of a one family dwelling. And what do they mean by that? That means on the outside of your house. You are required to have at least one receptacle front and back. And you have to have at least one receptacle, shall be installed within the perimeter of any balcony, deck, or porch. So if you go through and do your little, like a little deck upgrade to your house or something like that, and you have no receptacle, like within that deck area or something like that, you're in violation of code. But the little things we learn. But that's really what the main gist of chapter 3 here is that we get introductions to our how do we size our start considering what are our mandatories, how we size the circuitry, what formulas we're going to use. And usually, like I say, we're not going to get really complicated. Your general rule of thumb with the with the lighting branch circuits, right? 3VA is our multiplier for that. And then we go through, and like I say, a lot of times you'd be able to look up within charts. You'd be able to go right down the chart and say, okay, I have X amount of square footage. I need X amount of lighting circuits and that kind of thing. But yeah, this basically gets us into the very beginning of being able to size, based on our plans, right? This is what every electrician that goes through that's going to do a job bid, you have to size everything. I got to figure out how much equipment am I going to need? What size is everything going to be? And then that way, well, remember, it's all part of your job bid. You got to keep costs to a minimum. Somebody is paying for this. Now, if the sky was the limit, let's go with the biggest service panel they make, and we'll go and wire this bad boy up, and we'll go with so many breakers that we won't even know what we're doing anymore. But in reality, that's not going to happen. We're going to keep this down to a minimum. We got to keep our cost factor down. That's why when we size this stuff, we got to size our wiring. And again, the wiring, you wouldn't think, but enough wiring, it adds quite a factor to how much cost we're going to be dealing with. And so we have to make sure that we have the right wire at the right size, right, with the right runs based on how much footage it's going to be running and all that kind of thing. We'll start getting into that a little more later too. We'll start doing our voltage drops. And in fact, next Monday, I have two exercises. One, you are going to figure out how many lighting branch circuits you're going to need, and we're also going to do some voltage drop calculations as well, where I'll have like given wire size over X amount of feet, and you're going to decide whether or not that wire is good enough to use for this particular run based on your calculations. Because sometimes you do have factors, and it's like if depending on the house size, you may if your service panel is way in the garage and you need to wire something way, and you got like a ranch style rectangular shaped house, right? That could be quite a long run to the complete other side of the house. So you have to be able to figure out, well, if I have a straight run going there, what's my voltage drop going to be, and is this wire size going to work for that? And you'll go through that, and then we'll have you do these calculations and start getting into this. And they won't be really complicated. The only thing we ever use here are basically it's on the cover of the Uglies book, right? Ohm's law, and the other one is Joule's law, where it's the P power is equal to voltage times current, and then Ohm's law is E is equal to I times R. But those are and just variations of that. But everything that we use is actually, as far as calculations go, is in the Uglies book. Voltage drop calculations, all of it. Now, there's, of course, an excess of information in the Uglies book because it tries to cover everybody. So, sometimes you might not ever use any of the information in this book, but there is quite a bit in there that you will. But that's pretty much what I have today. And it's stop sharing. If anybody has any questions on like the homework or anything, the drawings all seem to make sense, I hope. I know chapter 2, structural features, is probably the more complicated one out of the whole bunch, and the only reason being is like these are other factors that sometimes you have to consider. There's like siding to the house you have to deal with if you're putting in outlets outside. It's like, what's the grade of the house, because you might have to figure out what height you're going to be installing outside outlets at, that kind of thing. Finished floors, you got to take into account how thick the finished floor is going to be. So there's always little factors that you're going to be dealing with that just aren't available on only the Electk prints. So we do have to look into some of the other prints, that deal with the other trades, just because of certain factors that we have to consider too. But that's the whole, chapter 2, structural features is usually my hardest one, but I like everybody to get into that because we're going to be using these. These are our prints. This is our house for this class. That's the house we're going to be building. So in a couple of weeks when we do our service entrance calculations, this is the house we're going to be using. So everything we do is going to be based on this house. So next week when I have this exercise together, for the minimum branch circuits for lighting, yeah, your square footage is going to come off your prints, and it's like, okay, how big's your house? How many lights you need? And we're going to figure that out. And we'll, and it's how many circuit breakers we're going to install to how many different lighting circuits we're going to have in this house. It'll be kind of fun. I know it'll be some of it's kind of a headache. I know, but that's all part of the learning process, right? Got to have a little bit of headache if we're learning, but I'll try to, there. I don't think that the formulas and stuff we use are too bad. Like I say, the super complicated ones are going to be figuring out these branch circuits, and then probably the voltage drop one. That'll be about the most complicated formulas we use, and then we'll go through later too, and we'll start doing where we figure out what our continuous duty things are in the house, where we have to add that 125% in. It's like what kind of things we consider, being continuous duty, just to get you familiar with everything, and because even if you're not going to be an electrician, you're going to be the HVAC guy. You have to be aware, okay, what parts of my HVAC equipment are going to be continuous duty? Because if I'm going to run the wiring circuit for this thing, I got to be able to size my breaker to the right size, make sure I'm running the right wire to my equipment, So basically, this has a little bit for everybody. I mean, some of it's, yeah, some of it might be overkill, but it's it's all good knowledge for going into the electrical field. Even if you're just planning on doing home wiring and stuff like that, you got to have your knowledge so that way you can do this stuff wisely. Like I say, go around based on the information you learned today and go around and look at your house. Does it follow these rules? Can you go along your kitchen cabinet and it actually has these dimensions to it? And it depends on when your house was built and when the stuff was put in. Now, a lot of it, like I say, the pre 1975 was like a biggie as far as like changes. That's when they had the 100 amp services coming in, because prior to that you had like 60 amp services with the screw in fuses, no circuit breakers and that kind of thing. But in this day and age, now we're dealing with the hundreds, the 150s and 200s. And in fact, they got some new homes that are going in now that are, I swear to God, they have 2 service panels. It's a 400 amp service going to these homes. And that's because more and more people are getting more and more toys at home. So the more toys you have, the more power you're going to use. Of course, having a 400 amp service, if I'm going to be using that kind of power, I wouldn't want to have the electric bill involved with that. But you'll see it. You'll see it. There's always changes going on. And I guess eventually we could have these really crazy big houses. But anyway. But yeah, does anybody have any questions? I mean, that's really mostly what I have today. Hopefully everybody's getting through everything okay. And I know the homework's, well, you got to remember too that the drawings weren't really considered a homework per se. That's more like a lab exercise. So yeah, I have labs, exercises that we'll be doing, and that's when I consider anything based on like the prints. When we're doing that kind of thing, that's kind of like a lab. And then the chapter homeworks, and then oh yes, I have a quiz assigned today, and I'm going to post the password up for the quiz. But for everybody here, if the password's wire, just all lowercase WIRE, and you get one shot. It's a take-home quiz. Yep, one shot, not like the homework. You get your answers are final, but you have open book. You can look at you should be able to look at your chapter 1 and 2 homeworks at this point, but it's a chapter 1 and 2 quiz, and that'll be assigned today. It's due by midnight tomorrow night. If anybody needs more time to that, I have been extending some of the homework times and stuff.
Is that the chapter 1 and 2 quiz?
Yeah.
You got posted for tomorrow?
Yeah, I got it due for 11:59 tomorrow. But like I said, if anybody needs more time, let me know. But I think that should be good. And it's like I said, it's just yeah, it's a one-shot quiz. You don't get, 2, 3 attempts or anything like that. You get one attempt, but it does have a password. Yeah, its password's wire. So when it comes up, it'll probably ask you, please enter your password, and then it'll let you in. And but yeah, if everybody could get through that quiz, and that
I have a
should,
question.
you have a question. I might have an answer.
Okay, the structural module that we did, was that considered a lab or a quiz or a test?
That was considered a lab.
A lab. Okay. All right.
Yeah, because well, see, usually, because that kind of exercise would have been one we would have done in lab actually, if we were at the school premises, because then we would have pulled out our prints and we would have all looked at it and everything. But yeah, it's considered a lab, and that's why based on the prints, I asked like, especially the chapter 2 ones where I asked about a lot of the measurements and stuff. But I want you guys to look at prints and be able to, go through and say, well, how far is this from there? And be able to look at it properly and go, yeah, it's this. And just get you used to dealing with, because, you're not, I don't expect you to build this whole house. You're not a carpenter. You're not a plumber. You can't be every trade. But it's just to consider how we do have to interact with the other trades. You know what I mean? Because you do have to consider certain factors. It's like, okay, so what is the foundation made out of? It's like, that kind of thing. So being able to look at that in a print and being able to pull it out is important, I think, because you don't just have to deal with just electrical. It's like there's phases involved in the course. I mean, you can't install a good portion of your stuff until the carpenters come in and frame the house, right? Because without the frame, what are you installing to? You know what I mean? So, but you don't want a finished wall either, right? So you have to come in after the carpenters frame the house. You come in and mount all your boxes, start pulling your wire and stuff like that, and then it's done in phases. And then when you're finished and the plumber's finished, then come the next guy, right? Now you got the plaster guys coming up, and they'll put up all the plasterboard walls, and we start getting more to the finish point. And we're still not done, right? Now we got to come back, and now we're going to mount in our devices. We're going to start putting in switches and receptacles, but we're still not done yet, right? Because now the painter's got to come in, and he's going to paint, so we don't put any of our cover plates on until the absolute end, because you don't want paint and plaster and other crap getting all over your cover plates, because that's a finished product. So there's, what I'm saying? So there's phases to this, and all these phases, you do have to deal with the other trades. You're one of the first ones there, because even if the house isn't framed yet, you still got to be able to provide a certain amount of power for the other trades to be able to use. So you'd have to, you're going to be pulling in your primary, and then, okay, now I got the panel in. I don't have anything else, but I have a couple of temporaries put in, for these tradesmen to be able to plug stuff, their equipment into. And then that's going to go away over time. But yeah, it's all about phases. And then, yeah, being able to read the prints, and you can determine that. It's like, okay, well, the concrete guys are going to come in and do this. So if I'm going to need anything in the concrete walls, I want to get there while they're framing up their stuff. Maybe I need to have a piece of pipe put into the cement wall here for this wire run or something. So I better get in there before the cement guys pour, right? So there's all little factors in being able to look at it. You have to, then you can determine when you have to do it and who you have to get into contact with. Because if it's an all brick basement or something like that, where it's all cinder blocks, well, then I don't have to worry about a cement guy and this kind of thing. You know what I mean? It's just little things, and it's little things from the prints that you should be able to pull out. So being able to measure stuff and being able to look at like details, like what's our finished wall made out of? Maybe I have to put an outlet in here, and depending on what kind of siding it is, it's going to determine what kind of box I'm going to use or something like that. Yeah, I try to get it, where you have to get a little bit of detail in this, or get, let's use our prints since we have them. Does that help? Does that, yeah.
Yeah. Thank you.
Oh, you're welcome. I know. I got the gift of gab, but yeah, chapter 2, structural features is probably one of the more hard ones that everybody struggles a little bit with, just because there is so much information I am asking for on that. But after this, it should be more straightforward. Like I say, a couple of weeks we'll have one I call the service entrance calculations, where you kind of basically you're going to size your panel. It's like, okay, what size panel am I going to need based on my power requirements of this house? So you'll go through and size up, like, and determine what size breakers you're going to need to feed your different branches to your house. It'll be fun. Might cause a few headaches, but like I say, when you're learning, you're supposed to have a little bit of a headache, right? But yeah. So no, that's where I'm leading to. Like I say, we do baby steps. So I'll introduce you to these new concepts, how to figure out, what branches are, what feeders are, how we size stuff, what kind of calculations we use to size stuff. And then, like I said, even with the new one today, where we consider what's continuous duty, and we'll get in more into that too. What are considered continuous duty, what kind of motors, and that kind of thing, so we can factor out all this stuff and be able to use whatever charts or calculations we're going to need to be able to determine what size we're going to have everything. Little by little, but yeah, we'll get there. And then, like I say, you guys go through that chapter 1 and 2 quiz, and I also got chapter 4 homework posted today as well. So, we got to keep, like I say, it's a lot of information over a very short amount of time. So I just got to keep everybody moving.
Is chapter 4 due Friday or is that Monday?
What's that?
Is chapter 4 due Friday or Monday?
Oh, let's see. I don't know. I have here. Chapter 4 is due Friday. You guys want it due Monday?
Yeah.
Give you the weekend. I just been throwing these out there, but yeah, let's do that because everybody's been asking me for extension. So, all right. So chapter 4 will be due next Monday at 1 o'clock. The quiz I have set to be due by tomorrow by midnight. And like I say, if anybody needs an extension on that, give me a holler and let me know, and we could probably extend it. But it's a quiz, so I want to, I think, what is that? It's like almost 30. Well, it's about 34 hours to give you guys to be able to do it. But so, any other questions from you guys, or you're all good? Silence means yes. No.
Yeah.
All right. Well, then I will. We're at Wednesday today, aren't we? Well, the time just flies. And I guess you guys have a good weekend, and then I'll see you Monday. But yeah, if you guys have any questions, get a hold of me, and we'll go over what you need and that kind of thing.
Sure will do.
All righty.
Thanks so much.
You're welcome. Oh.